Hi, so let's talk about an adiabatic process. In this particular example, we have 8.5 moles of gas that are expanding adiabatically, performing 8,300 joules of work. Determine the change of temperature of the gas. So first of all, let's take a look and say that I'm going to look at my PV diagram. And so I'm going to have a P1 and a P2 and a V1 and a V2, and I am expanding adiabatically. And adiabatic is a nice steep curve here. It's not a straight line. I can't actually determine the work of this because we don't have that level of math in this course. For this, you're going to need some serious calculus. And that's okay, but we just don't have it yet in this course. So we've got a steep. In fact, adiabats are steeper than isotherms. And so this is a steep little thing that's going on here. Now we know that we're expanding. So we went from V1 to V2. We actually expanded the gas. We don't know the volumes. We don't know the pressures. But we are performing 8,300 joules of work. And that means that this is work done by the gas. And so the work is going to be negative because we always define work on the gas. Because the work being done by the gas here is positive, and so the work done on the gas is negative. All right, so I've got 8.5 moles. That's going to be my N, and I really want delta T. Okay, so I've got PV equals nRT, and that's cool. I got that, except that I don't really need that. I don't know P, I don't know V, so I can't use this equation. What I do know is that delta U is 3/2 nR delta, shoot, let me fix that, delta T. And so if I find my delta U, I can find my delta T because my delta T is 2/3 2/3 nR delta U. Okay. Not too shabby. We've got this. So I've got delta U. Well, what I do know is delta U is Q plus W. And this plus is work done on the gas. So we're going to say that the work is going to be negative 8,300 joules because we define our work as being done on the gas. Okay. Adiabat means that my Q equals 0. That's the big idea in this problem, is that the adiabat says that there is no heat flow from the vessel to the outside of the system. So I can have a temperature, but it's not leaving my system. It's staying isolated. And so if I'm doing work and it's not leaving the system, the temperature of the system must change. Well, so let's see what's going on here. Delta U is going to be W, which in our case is negative 8,300 joules, and delta T is 2 delta U over 3 nR, and delta U is equal to negative 8,300 joules. So our temperature is going to go down. Okay, that should make some sense to us. The pressure went down. We're not changing the heat. The heat isn't flowing outside the system. Since it expanded, the temperature would decrease. Okay, so my temperature, delta T, is going to be 2 times negative 8,300 over 3. Now my number of moles was 8.5, and R is 8.314 joules per mole Kelvin. And since I've got the right set of units here, I'm good to go. And I'm going to bring out my handy dandy calculator because I didn't do this in advance. Shame on me. So I've got 2 times 8,300 divided by 3 times 8.5 times 8.314. And I get 78.3 joules. So it's going to be negative 78.3 joules. Not joules, sorry, shoot. Gosh darn it. That's going to be Kelvin. I have lost my mind here for just a second. So yeah, there should be my change of temperature. Whenever you're dealing with an adiabat, you have to remember that the Q is 0. The work is then going to be equal to the change of internal energy. I can't use a PV equals nRT because this is a curve, and that's an adiabat. And my pressure and temp volume are both constantly changing. And so I can't use a simple relationship there. It's not just a work equals pressure times change of volume. Since they're both simultaneously changing, we need more powerful math than we have at our hands right now. Okay, so remember how this works. Our next example will be an isothermal example, and then we'll do another PV diagram example. And just keep working, and remember that we're all in this together.